In the name of Almighty God, I am Mahsa Hassankashi, and today I want to talk about Chladni plate. A Chladni plate is a device invented by Ernst Chladni to demonstrate how sound vibrations create visible patterns on a flat surface. It consists of metal plate with a fine granular substance like sand sprinkle on it. When the plate is vibrated at a specific resonant frequency, either by bowing it with violin bow or using a speaker driven by a frequency generator, the granular material is tossed from the areas of high vibration or antinodes and collects it in the spots where the plate remains still, forming intricate symmetrical patterns. And you can see the resonance between valves and RC circuit. And how it works, plate and granules. A metal plate, typically square or circular, is covered with a thin layer of sand or other fine particles like lycopodium, powder, or salt. The next is vibration. The plate is made to vibrate. This can be done by drawing a violin bow across its edge or by attaching it to a speaker that is fed a specific tone from a frequency generator. The next is node and antinodes. Sound waves cause the plate to vibrate in a pattern of standing waves. Resonant frequencies. Resonance frequency is the natural frequency at which a system vibrates with the highest amplitude. When an external force matches a system's resonant frequency, the vibration amplifies significantly, a phenomenon called resonance. This concept applies to everything from a swinging pendulum to complex electronic circuits and is determined by an object's physical properties. And how it works. The first one is natural frequency. Every object has one or more natural frequencies at which it will vibrate if disturbed, such as a tuning fork or the string on a guitar. These frequencies are determined by the object's physical characteristics like its mass, stiffness, and size. The next chapter is energy transfer. When the frequency of external force matches the resonance frequency, energy is transferred to the object very efficiently. This causes the amplitude of the vibration to increase with each push or cycle. The next is amplification. This continuous amplification can lead to a dramatic increase in vibration. For example, a person pushing a swing at the right rate will make it go higher and higher, while a bridge can be destroyed if its structural resonance is matched by external vibrations like marching soldiers, a now historical cause of bridge collapse. Examples of resonant frequency. The first one is mechanical system. A string is a simple example. Its resonant frequency is determined by its length, and pushing it at that frequency is most effective at building its height. The next one is acoustic. A wine glass can shatter if a singer matches its resonance frequency. In speakers, specific parts have resonant frequencies that determine their best for performance. The next is electronics. In an RLC circuit, resistor, inductor, capacitor, the resonance frequency is the point where the circuit's capacitive and inductive reactances cancel each other out, resulting in a maximum oscillatory response. This is the basis for tuning circuit in radios and other communication devices. Resonance is a phenomenon that happens when an object or system is subjected to an external force or vibration force and frequency matches. A resonance frequency or resonance frequency of the system defined as a frequency that generates a maximum amplitude response in the system. When this happens, the object or system absorbs energy from the external force and starts vibrating with a larger amplitude. Resonance can happen in various systems such as mechanical, electrical, or acoustic system, and it is often desirable in certain applications such as musical instruments and or radio receivers. However, resonance can also be detrimental, leading to excessive vibrations or even structural failure in some cases. All systems, including molecular systems and particles, tend to vibrate at a natural frequency depending upon their structure. When there is a very little damping, this frequency is approximately equal to but slightly above the resonant frequency. When an oscillating force, an external vibration, is applied at a resonant frequency of a dynamic system, object, or particle, the outside vibration will cause the system to oscillate at a higher amplitude with more force than when the same force is applied at other non-resonant frequencies. The resonance frequencies of a system can be identified when the response to an external vibration creates an amplitude that is relative maximum within the system. Small periodic forces that are near a resonance frequency of the system have the ability to produce large amplitude oscillations in the system due to the storage of vibrational energy. Resonance phenomena happen with all types of vibrations or waves. There is mechanical resonance, orbital resonance, acoustic resonance, electromagnetic resonance, nuclear magnetic resonance, electoral resonance, and resonance of quantum wave functions. Resonance systems can be used to generate vibrations of a specific frequency. For example, musical instruments or pick out specific frequencies from a complex vibration containing many frequencies. For example, filters. The term resonance originate from the field of acoustics, particularly the sympathetic resonance observed in musical instruments. For example, when one string starts to vibrate and produce sound after a different one is struck. Resonance happens when a system is able to store and easily transfer energy between two or more different storage modes, such as kinetic energy and potential energy in the case of simple pendulum. However, there are some losses from cycle to cycle called damping. When damping is small, the resonance frequency is approximately equal to the natural frequency of the system, which is a frequency of unforced vibrations. Some systems have multiple and distinct resonance frequency. For example, a familiar example is a playground swing which acts as pendulum, pushing a person in a swing in time with a natural interval of the swing. Its resonant frequency makes the swing go higher and higher on maximum amplitude, while attempt to push the swing at a faster or slower tempo will produce smaller arcs. This is because the energy the swing absorbs is maximized when the pushes match the swing's natural oscillations. Resonance happens widely in nature and is exploited in many devices. It is the mechanism by which virtually all sinusoidal waves and vibrations are generated. For example, when hard objects like metal, glass, or wood are struck, there are brief resonance vibrations in the object. Light and the other short wavelength electromagnetic radiation is produced by resonance on an atomic scale, such as electrons in atom. Other examples of resonance include timekeeping mechanisms of modern clocks and watches. For example, the balance wheel in a mechanical watch and the quartz crystal in a quartz watch. The next one is tidal resonance of the bay of Fundy. The next is acoustic resonance of musical instrument and the human vocal tract. The next is shattering of crystal wine glass when exposed to a musical tone of the right pitch. Its resonance frequently. The next is friction idiophones, such as making a glass object, glass bottle, or vase vibrate by rubbing around its rim with a fingertip. The next one is electrical resonance of tuned circuit in radios and TVS, what that allow radio frequencies to be selectively received. The next is creation of coherent light by optical resonance in the laser cavity. The next is orbital resonance as exemplified by some moons of the solar system, giant planets, and resonance groups such as the plutoniums. The next is material resonances in atomic scale are the basis of several spectroscopic techniques that are used in condensed matter physics. The next is electron spin. The next is electro spine resonance, and most Bohr effect and nuclear magnetic resonance. And what about the linear systems? Resonance manifests itself in many linear and nonlinear systems as oscillations around an equilibrium point, which the system is driven by a sinusoidal external input. A measured output of the system may oscillate in response. The ratio of the amplitude of the output's steady state oscillations to the input oscillation is called the gain, and the gain can be function of the frequency of the sinusoidal external input. Peaks in the gain at certain frequency correspond to the resonance, where the amplitude of the measured output oscillations are disproportionately large. Since many linear and nonlinear systems that oscillate are modeled as harmonic oscillators near their equilibrium, a derivation of the resonance frequency for a driven damped harmonic oscillator is shown. An RLC circuit is used to illustrate connections between resonance and the system's transfer function, frequency response, poles and zeros. Building of the RLC circuit example, these connections for higher order linear systems with multiple input and output are generalized. The driven damped harmonic oscillators. Newton's second law takes the form: consider a damper mass on a spring driven by a sinusoidal externally applied force. Newton's second law takes the formula of uh, itself, and where the m is the mass, x is the displacement of the mass from the equilibrium point, and f0 is the driving amplitude, and omega is the driving angular frequency, and chi is the spring constant, and c is the viscous damping coefficient. The general solution of this equation is the sum of the transient solution that depends and a steady state solution that is independent of initial conditions and depends only on the amplitude f0, driving frequency omega, and undamped angular frequency omega 0, and the damping ratio as tau. The transient solution decays in a relatively short amount of time, so to study resonance it is sufficient to consider the steady-state solution. It is possible to write the steady-state solution for Xt as a function proportional to the driving force with an induced phase change. Thank you so much for watching my video until the end, and also you can see the RLC and how the inductor and capacitor can neutral themselves and make a resonance. And here there is an application, and can uh, run it by applying it, and after that compute and press the compute, and there is a resonance here from the frequency. Also, you can download this application from my github.com/mahsa